Yeah, I'm Bhavik Mehta from Cambridge. I'm going to be talking about formalizing Sharkovsky's theorem, and this is a proof problem. So Sharkovsky's theorem is a result in dynamics. It's fairly elementary result in discrete dynamical systems. And one thing I want to highlight is that it only uses undergraduate real analysis. So it's got fairly low prerequisites. The original result was one of the earliest steps in chaos theory. The papers which it inspired and which came at around the same time were the things that kind of sparked the popularity of chaos theory throughout maths. What I'm going to be presenting is the first formalization of this theorem in any proof assistant. But what I really want to do is exposit a new formalization of an elegant but also elementary piece of maths. And along the way, I want to show some of the joys and the pains of formalizing actual maths. So hopefully, for those of you who have formalized some maths before, this will be familiar and hopefully not too painful. And for those who haven't formalized maths before, it'll give you a flavor of what it feels like. So one of the things I'm trying to be cautious of when doing a maths talk is that I don't give you too many definitions. I've only got two in throughout the whole thing. Here's the first one. Let's say I've got a real valued function. Then a point has period n, if n is a positive integer, as long as the nth iterate of f is x. So the superscript n here is the iterated function, not a power. And that's what it will mean throughout. So this is if a point has period n, and a point has minimal period n if it's the smallest thing with that period. Makes sense. Now, Lee and York in 1975 proved that if you have a continuous function and a point which has minimal period 3, then there's a point of any minimal period. So that means if I have a point with minimal period 3, then there's a point with minimal period 5, minimal period 10, minimal period 1, in particular a fixed point. They also showed that there are uncountably many points which are chaotic. And this inspired the title of the paper, which was Period 3 Implies Chaos. But unbeknownst to them, their first theorem was actually proved more generally 11 years earlier by the Ukrainian mathematician Sharkovsky. So he showed the original result that 3 implies anything, and he also showed that 5 implies anything other than 3, and much more. So that's the theorem I'm going to be talking about. I've written down this notation exists MP, which is just my shorthand for there exists a point of minimal period. So exists MP5 at the bottom there means there exists a point of minimal period 5. Because that thing is going to show up so often, I'm just going to condense that bit. Okay, so what does this theorem actually say? Sharkovsky defined an ordering, a non-standard ordering on the positive natural numbers. His ordering starts by taking all the odd numbers in increasing order, then double all the odd numbers in increasing order. So we take all the odd numbers, and then after all of that comes 6, then 10, then 14, and then double that, and so on. So we've got all the odds, then double all the odds, then double that, all the way up. Now, the only thing that you might notice is left is the powers of 2. So we're going to put them in at the end in reverse order. So this is a slightly weird ordering, but it is going to be the right ordering. And so I think you can see why I've called it a non-standard ordering. So again, we've got all the odds, twice the odds, 4 times the odds, and so on, and then the powers of 2 in reverse order. Now, it's a linear order, also known as total order. It's not a well order, but it does have one important property right now, which is that 3 comes first. And as we'll see, this is why period 3 implies any other period. It's purely because 3 comes first in this ordering. Also, I mentioned that Sharkovsky showed 5 implies everything else except for 3. It's because 5 is second in the ordering. So Sharkovsky's theorem actually says, let's say I've got an interval, not necessarily closed or bounded. If you like, you could just pretend I is the whole set of real numbers. But the theorem will actually work for any interval. So I've got a function defined on a real interval, and it's a continuous function. Then if I have a point of minimal period m, and m comes before n in the Sharkovsky ordering, then there is also a point of minimal period n. Another way of saying that is the set of minimal periods of f is upwards closed in the Sharkovsky order. So I'll bring the ordering back up again. So like I said, this means if you have a point of minimal period 3, then you have a point of minimal period, say, 14. Another consequence of the theorem is that if you have a point of period 2, so basically a point which goes back and forth, then you've got a fixed point. That's a much easier theorem than the general thing, but it does come out of this. Another consequence is that if I have a real valued function which has finitely many fixed points, then all of the fixed points must be powers of 2, because otherwise I would be included in this infinite range. So that's all consequences of Sharkovsky's theorem. So I think it's a pretty impressive theorem. What's even cooler is that that's not all he proved. He also had the converse. So I'm going to call the forward direction the forcing theorem. That's what it's sometimes called in literature, because some periods force other periods. And the converse, the realization theorem. This says that if I take an upwards closed set of the Sharkovsky order, then it will be the set of minimal periods of some continuous function. So as you can see, this is the exact converse of the line I've written for the forcing theorem. So it's that if I have an upwards closed set, then there is some function which realizes that as its set of minimal periods. And if I have some function, then the set of minimal periods is upwards closed. So these are the two, this is the theorem I'm going to be talking about, and these are the two parts. What are the ingredients for this proof? Because it seems like a pretty impressive proof. But it turns out that there's very little involved. The hardest theorem we need is the intermediate value theorem. So the way I've stated it here looks a bit weird, but just trust me for now. If I have a continuous function and f of a times f of b is negative, the reason I've written like that is I want to emphasize that f of a and f of b needs to be different signs and neither of them can be 0. But it doesn't matter which way around they are. So f of a and f of b are different signs, not both 0, and yeah, on either side. Then there's a point in between a and b which hits 0. This is a hopefully familiar theorem to everyone from analysis. Now it has one very important consequence, which I'm going to call the fixed point lemma. I won't give you its proof. It's a very easy exercise. It's essentially just saying that if I have a continuous function on AB, and f sends AB to something slightly bigger than AB itself, then there's a fixed point inside AB, sorry. So the intuition I want to give you for this is, suppose I have my interval here, A and B. I apply f, and these points are going to go in different directions. If they go in different directions, doesn't matter where, as long as they go in so they can't go in the same direction, they have to go in different directions, then there's a fixed point at that interval. That's what the fixed point lemma is saying. And these are the two things we'll need throughout, that's all we'll need. And the second one is an easy consequence of the first. Okay, so now let's actually talk about the formal proof. Let me talk about stating the proof, stating the theorem even. The only hard part will be defining the order, because as we saw, it's a very strange looking ordering. I won't go through the details of how it works. You can see the paper for that. But the main slightly odd thing is that the natural numbers in line include 0. And the order as I wrote down didn't include 0 anywhere. So there are a number of solutions. I could define the type of Sharkovsky natural numbers, or the positive natural numbers, to just not include 0. I could choose to put 0 at the bottom of the ordering. I could choose to put 0 at the top of the ordering. I could choose to make it I forget the word off the top of my head. Incomparable, there we go, incomparable with every other natural number, or I could slot it somewhere random in the middle of the ordering. All of these would make some sense. It turns out that the most natural one is to put 0 at the bottom of the ordering. And then lots of my theorems will say n is not 0 where appropriate. So I've got this first example, the theorem that 3 is less than everything in the Sharkovsky ordering. I now need the condition that n is not 0. There are a number of reasons why this is the most convenient choice, but any of the choice I mentioned earlier would work. It just turns out this one's the easiest to work with. And I've got some information in the paper about that if you're curious. So like I said, I've omitted the definition of the ordering here because it's not that interesting. But I have shown some consequences of it. So the second one here is essentially just a proof that the powers of 2 are in reverse order. That's what you can see in that statement there. Another thing is a consequence of the definition, which isn't completely obvious, but makes sense when you think about it, which is that whenever you double things in the Sharkovsky ordering, it keeps it the same. So as we saw, when you take the odds and move it down, it stays the same, but also in the powers of 2, it stays in the same order. Okay, I can now double check that the definition I have is correct. So what I did is I added some lemmas to lean simplifier. List.chain here basically says, we'll take this list of things and check that pairwise everything that works. So this is notation for 3 is less than 5, and 5 is less than 7, and 7 is less than 9, and 9 is less than 6, and so on. And I can prove that just by sim. The simplifier will work it all out and check that everything makes sense here. The reason I've written the new lines in this way, by the way, is because we've got the odds, then double the odds, then quadruple the odds, and then the powers of 2. Okay, so now what's the actual proof like? Well, it's surprisingly easy. So least the proof of the forcing theorem. So the ingredients I gave you earlier were the intermediate value theorem and the fixed point lemma. The intermediate value theorem is already in Lean's MATLAB, so I don't have to do anything there. I got lucky. The fixed point lemma is actually very easy. I mentioned it's an easy exercise. That wasn't just me lying as a mathematician. It is just 5 lines of Lean. But one other thing which is going to be really useful is switching between points of minimal period and orbits of size n. So the difference here is if I have a single point with period n, then I sometimes want to think about the collection of points which that one hits, which is also called the orbit. So I've started with my point here. Maybe it has period 5, so it hits 5 different points. And I want to consider that as a set. Now, these are conceptually the same thing, but one is a set, one's a point, so I do need to have different things here. And here's just a definition of what the cycle is. And what it turns out, because even though these are equivalent, it turns out to be easier to have cycles in our assumptions and our conclusions to be about points of minimal period. So that's how all the proofs are going to be laid out. Now, what does the proof of the forcing theorem actually look like? It splits into 5 parts. I won't go through all of them, but I should say there are many possible proofs. There's one paper alone which gives you 8 possible proofs, and then another paper by the same author which gives you 6 more. And then there's the 2 original papers I talked about earlier by Sharkovsky and Lee and York, which also give different proofs. So there are many different options. I just chose the one which I think is the nicest. But this one, as I say, breaks down into 5 parts. The first part is very easy. If there's a point of minimal period 2 and there's a point of minimal period 1. I mentioned that earlier was a special case, but it does actually need to be done as its own thing for now. Part B, if I have a point of minimal period m, where m is at least 3, then there's a point of minimal period 2. Then the same thing, where m is odd, then I can get to plus 2. And then if on the same conditions, I can get 6 and 2m. And then the final part is from those 4, you can stitch everything together to get the forcing theorem. Now, it doesn't look so clear why these things are enough to get that weird ordering back, but firstly, they should be enough because the realization theorem said that I have an if and only if, so it must be the right order. But also, I'm just going to try and give you some sort of flavor of why this makes sense. Now, like I say, A is very easy. C and D, maybe from the statement you can already tell, are a little bit more difficult. So I won't go into the details of those. You can see the code for that. What I will do instead is talk you through the proof of part B and part of the proof of part E. And the actual details of part C and D, it's essentially the same thing I'm about to tell you for B, just with some induction, with some more details, with a bit more time. But the idea is essentially the same. OK, let me show you the statements first. So I've got a odd connected I. That's just a way of saying it's an interval. Then a continuous function, and f maps I to itself. Then I have my cycle, because remember I said that I'm stating all my theorems where the hypothesis I have a cycle. And the conclusion is, well, either the fixed point or the point of minimal period. And m here is now translated to be p.card, which is the cardinality. Now, one thing which is a bit awkward is the proof on paper that I followed. For all the first 4 parts, A to D, it started in the same way with the same definitions, but then finishes differently. So in terms of formalizing this, there are 2 completely obvious things you can do. One is start your code the same way each time in the copy-paste. Or you could have one massive proof which has all 4 as conclusions. They're both pretty bad, so I think the natural solution which anyone would think about is taking the core, which is common to all 4, take that out and use that. So that's what I did. It turns out that the core gives you a really ugly looking statement, not nearly as nice as these ones, but I think from an engineering point of view, it's pretty clearly the right choice. So what does proof actually look like? So remember what I'm trying to prove right now is that if I have a point of minimal period m, then I have a point of minimal period 2. And just for the sake of simplicity, I'm going to say m is 5. But the proof I give you will work for any m greater than 3. I'm just going to show you for 5 because it's easier to demonstrate. So I have a point of period 5. In particular, I have a cycle, which has size 5. I'm going to call the cycle P. And then this point at the bottom is the minimum point of P. B will be defined by f to the 4 of min P. The reason I've used 4 here is because it's m minus 1. So the key thing about B is that it maps to the minimum of P. Now, I claim that there must exist an A in between these 2 points, where when you hit it with f, you end up above B. Why is that true? Well, if not, then when you apply f to min P, you go up. If you apply it again, you must go up because I'm still within this interval by contradiction. But then as you keep going, you eventually get back at B. But that's not what we wanted because we said that for every point inside this interval, you must be below B. So there's a contradiction, and I can find my A. So here's my point A, and it lands above B when I hit it. Now, by the fixed point lemma, there's a point in between A and B, which is a fixed point. The reason for this is that A has gone up and B goes down. I've got 2 points going in opposite directions, so there must be a point between them, which is a fixed point. And then I can use the intermediate value theorem to find a V in between A and Z, which hits B. That's because A lands above B and Z lands below B. So there must be a point in between, which hits B. I think you can see the sort of ideas which we're going for here. Now, I do the same thing with f squared. So I should say f iterate with itself. If I apply that to min p, it goes up because p is the minimum. And if I apply it to v, it goes down. So there must be some point in between, which I've called y, which has f squared of y is equal to y. So this point is the one which I want to be my periodic point, because I hit it twice with f, and I've got back to where I started. But I don't yet know that y has minimal period 2. I just know that it has period 2. But since I know that such a y exists, I'm going to choose the maximal one, and it turns out that that's the right choice. In the paper, I explain why that's the right choice. I'm not going to do it now because everyone will fall asleep. But essentially, this is the right choice, and you can prove it works. So that's what the proof of part B looks like. Doing A and B together takes about 120 lines. That's including the shared core, which I took out. C takes about 90 lines. C is a little bit harder than A and B together, so which kind of makes sense from these calculations. But one thing which is really useful here is that it's important that M is odd. So there's lots of stuff that you need to worry about with where the odd and even numbers are. And Lean's automation for parity simps makes that a lot easier. Part D, on the other hand, is quite a bit worse. It's a subtle double induction, and the induction hypothesis was never properly written down. It was kind of implicit in what was in the text, which I think hopefully sounds familiar to some people who formalized stuff before, when there's an induction hypothesis which is never quite clear until you formalized it. But other than that, it wasn't too bad. So I'm going to quickly give you an example of E as well now. So from the earlier things, I never showed why 6 is less than 10 in the Sharkovsky order. There are, again, a number of details. I'm only going to give you a special case. But this is the sort of idea which all of the others follow. So I'm going to try and prove that if there exists a point of period 6, then there exists a point of period 10. So if M is minimal period if 6 is the minimal period for f, then 3 is the minimal period for f squared, because I've just iterated. Then, by part C, I can add 2, and 5 is the minimal period for f squared. That means either 5 is a minimal period for f, or 10 is a minimal period for f, because I have a period of f squared. In the case of 10, then I'm happy. That's what I wanted the whole time. But if I have 5, then I can use part D to get the 10 I needed. So in both cases, I'm happy. So that's what that proof looks like. So how did it actually go in practice? Some parts were really nice. Doing the real inequalities, on the line I showed you, it had points moving up and down, and it was very important what landed where. So dealing with the real inequalities was really nice to do in Lean. I don't think any of that is specific to Lean. It's just how well can you handle inequalities. Doing the parity calculations was really nice, and there were some existing lemmas for dealing with minimal periods, and like I mentioned, for the intermediate value theorem, which made my life a lot easier. But there was one thing which was incredibly annoying, and that's, so at the end here I mentioned I've got a point which is a minimal period for f squared, and therefore I know that I have 5 or 10 as a period for f. And there's one particular part of the generalized version of that, which looks like this horrible looking statement for natural numbers, which is something like if I've got 3 natural numbers which are not 0 and s divides k times n, then when you divide this by the GCD of that with something else, then you get k, therefore you get some, it's horrible, but it does need to be done. And what's most annoying is that in all of the places the proof is written down, in textbooks or whatever, this sort of thing is never explained. And maybe it doesn't deserve to be because it's just a number theory thing, so maybe you don't want to go into elementary number theory in the middle of a dynamics book, but it is something which needed to be done. Now this admittedly only took about 14 lines, so it's not actually that bad, but the reason I want to highlight this in particular is that it has the worst ratio, the De Broglie ratio, because it just wasn't mentioned. It's 14 over 0. And that sort of thing happens sometimes when formalizing maths. Okay, and here's what the final statement looks like. So like I mentioned, it's incredibly straightforward to formalize, except for those 2 specific points, that awkward double induction and this really annoying natural numbers thing at the end. So I'll just mention these two final things at the end. So I have, if I have a point within the interval which has minimum period n, then I have a point which has minimum period m under the condition that n is before m. So hopefully that is a fairly clear translation of what I claim to be proving. So what about the realization theorem? Well, the realization theorem says there is a function which gives you this particular set of minimal periods. So I need to make the function. One thing really nice about this is that the family of functions you get for any particular set of periods can be parameterized really nicely. And they're all the th is written here. It turns out that as you vary the parameter h, the map you get, just by drawing this, will be exactly the function that you're looking for in the theorem. So hopefully it's fairly clear what the definition of the map th is, but just to lay it out clearly, I've basically got the triangle here, which is 2x for x below half, and then the reflection of that, and I just truncate it. Sometimes these are called truncated tent maps, but also it just looks like a tent. There's the formal definition, and to prove it's continuous, it's just 2 lines of lean. I write by continuity, and I'm happy. And there are 3 important properties that you need to prove the things we want to about these functions. Firstly, T1, which is the important, they'll all be important, but T1 has special importance. So T1 is this one where you don't need to truncate at all. That has a 3 cycle. Now that's fairly easy to prove. In fact, it's incredibly easy to prove. It's just numeric calculations. So I put it into lean. I can use lean's norm num, which is a numeric normalizer, and that's very easy to prove. And since we now have the forcing theorem, I can also show that it has a point of every minimal period, because 3 was first. And then the next thing I need is that T1 has finitely many points of any possible minimal period. I want to come back to that point in a second. I'll just quickly talk about the third one. Now, the way I've written it there is kind of unclear, but that's mostly because I don't want to go into it in too much detail. But the basic idea is that if I increase h, then any cycle, all of whose points will lie below h, remains a cycle. And if I decrease, if I have a cycle for k, and all of the points that are in the cycle are below h, then if I reduce k to h, then everything remains a cycle. So essentially, all this is saying is, as you change the parameter, can I control the cycles? That's all this lemma, that part 3 is saying. If my explanation made no sense, that's completely fine. It's just saying, as I change the parameter, where do the cycles go? Once I have those things, then I can write down this definition. Now, again, it's not so important what the definition is, except for the fact that I'm taking a minimum over the set of cycles. And naively, that might not be well defined if the set of cycles is infinite. So I need to make sure first that the set of cycles is finite, and that's exactly what point 2 here was doing, because it said there are finitely many points of every possible minimal period. Okay, so now that this definition makes sense, gluing all the bits together that I had on the previous slide, we get the theorem. And this is full Sharkovsky theorem for the real numbers. I'll go through it one more time. If there exists a function, a continuous function with S as a set of minimal periods, if and only if that set is the upper set of the Sharkovsky ordering. There are also some other versions which you can prove, which I went into in the paper, but I won't talk about that now. And this is actually very straightforward to prove, except for the couple of points I've highlighted. There's one slight subtlety which I didn't mention, which is the powers of 2, because of the way the ordering works, because the powers are true in reverse order. There is one upper set which is kind of special, because it's infinite and doesn't have any least point. But it turns out that's still fine. You do a continuity argument. It's not important. The hard part is showing that this finitely many thing happens. The reason it's hard is because the proof on paper is inspect the graph. That's all you get on paper. So there's the graph. I invite you to inspect it and see why the thing is true. And hopefully, a couple of people might be realizing why it is true. And that's because the line I've drawn through the middle here, that's the graph of f of x equals x. And every point of minimal period n must be a fixed point of t1 to the n, and there are finitely many of those. But we still need to prove this. It's a picture. So the proof strategy is essentially break this graph up into a number of straight line segments. Inside each straight line segment, you must have at most 1. It turns out you actually have exactly 1. And so you have exactly 2 to the n fixed points of t1 to the n. So you have 2 to the n point of period n, and every point of minimum period n must be a point of period n. So I have 2 to the n many. Now this took 260 lines for something which on paper was inspect the graph. So this is a ratio of 260 to 1. Not ideal. Okay, so in conclusion, what I want to show you was a formalization of a piece of math which hasn't been verified before, in particular, beginning of chaos theory and simple dynamical systems in Lean. I should mention quickly that this isn't the first time any chaos theory has been formalized. It's not the first time any dynamical system has been done in Lean, but it is the first time this theorem has been done in any proof resistant. But in particular, I want to highlight some of the source of difficulties and some particularly elegant subproblems which showed up all from this one nice self-contained theorem. I used mathlib heavily throughout this, dynamics, finite sets, real analysis in particular, and some feedback, I guess, for Lean's automation. Really nice for topology, really nice for simplifying, really awkward for natural numbers in what I needed it for here. In the future, the rest of the Lee York paper, doing actual chaos theory rather than just the beginnings. Sharkovsky's theorem does generalize to some other spaces, not many, but a few, so that would be nice. And doing the same thing in other proof resistance, because nothing I did here was specific to Lean. I think some of the feedback and some of the experience might be, but I'd be really interested to see how this looks in other proof resistance as well. Thanks very much.
We can have a couple of questions. So any questions? Oh.
What do you think about the difference of using sort of the simplifier or norm num or other sort of normalization tactics versus sort of in-kernel computations like deck trivial? Do you think it would be better or easier if Lean had better sort of support for in-kernel computation?
That's a good question. So I mentioned earlier that I used sim to try and check the stuff about the Sharkovsky ordering being correct. The first time around, I actually did try and use deck trivial to do those things. And it does work. The thing is then it forces all your definitions to be computable. And that's not necessarily a bad thing if you like having computable definitions, but it is slower, at least in doing it in Lean. It also means that you need to tailor the definitions in very particular ways so that they compute quickly. Whereas if I use the simplifier, I get to choose how the checking process works, rather than being restricted to what the kernel computation does. So that's why I chose to use sim, because I'm allowed the flexibility in how the process runs. I think if kernel reducibility in Lean was faster, then I might have taken a different choice, but I still wouldn't have the flexibility that I like having with sim.
Any questions? Then let's thank the